well, first of all, I'd like to thank the organizers for inviting me, and say how happy I am to be here. And so Javier told me this should be a mini course directed to the grad students, and that's what I'm going to do and how I designed this. So there'll be 3 lectures on it. So today will be. My intention today is to start presenting whatever you know in a crash course on algebraic topology. So in 1 hour, you're going to know everything you want to know about algebraic topology. So, but the idea is to try to make you see all objects from a different perspective, at least. And that will motivate what comes in the last lecture when I try to explain Horvath's motivic complexes and his approach to motivic cohomology. And the second talk will be a hybrid between the purely topological and this more algebraic, and there'll be some ingredients coming from differential geometry where we employ some objects that live there to represent cohomology from a different perspective and point of view. That will tie into things that we're trying to the joint link with James that we presented in the last in my talk in the conference. So as I said today, I mean, please, the algebraic topologists is in the room for you for the first half an hour. But the idea is that we're going to talk about revisiting. So this is part 1. I'm going to be revisiting all numeric cohomology. So. And so when I write top, I mean the topological spaces. When I write top star, the category of spaces with a base point. So there's a category of base spaces. And so let me introduce some notation here. So if you have 2 basic spaces, then you can take this mass product. It's just the result of taking the product and dividing, smashing. So in particular, we can talk about, so when you smash the circles, you have a sphere S2, etc. And this is actually very innocuous statement. Is a good exercise. I hope you have not seen this. If you have p copies of the circle and you smash them, you get a sphere SP. And a lot of what we're going to be discussing, in some sense, revolves around the sphere and what you can do with spheres. And in particular, this presentation will bear relevance in what comes next in algebraic geometry. So now let me recall how you define single cohomology. So very briefly, the idea is that, and what I want to do is to bring this idea that you live in the world of topological spaces, and then you send topological spaces to another category, and you assert a homological algebra there. It's not a given category. So but now, next, in my next lecture, I'm going to do the same, but with a different category from what you're used to. So, so the idea is that you start with the topological spaces, right? And so you have this space here, and then you look at the thing. This is a simplicial set, but where sing sub n of x is simply the set of all maps from delta from the simplex to x, the collection of all such maps. And then, of course, you look at the free abelian group on it. This is a simplicial abelian group. And then anytime you have a simplicial abelian group, whatever that is, you can take the alternating sum of the faces, and then you get what we're used to, which is the singular complex. the single complex of X. But now I want to see a single complex as a cohomological complex greater than negative degree. So in other words, I have here 0, minus 1, minus 2, minus 3, and so I have my C0 of X here, C1 of X, and I have the usual differentials that you have. But I want to see them all greater than negative degrees, so the grades go up. So for me, everything goes, you know, all the complexes are homological complexes. So, but now you think about look at the, let's call KOM, the category of complexes of abelian groups, and let's think about, in this world, you have a notion of homotopy of complexes. So you have a homotopy of maps of complex, so you have a homotopy category of complexes of abelian groups or complexes in any abelian category. And so you have so we end up getting a functor from here to here. Right? That's the single complex functor. Now let me give you an object that lives in this category. For example, so another notation. So if you start with a complex A, and by A I mean something that, now actually I want this category, let's think about complexes that are bounded above, maybe. So in other words, A goes something like this. This is AN, goes AN plus 1, goes AN plus 2, and it stops at some point. And then if you have such a complex, then you have R, which is an integer, right? James already used this in his talk, but I'm just reminding what that means. This is shifting a complex by R. So this is another complex, but now the jth abelian group in this complex is the R plus jth complex in the previous complex. I'm just shifting the complex depending on what R is. In particular, it's supposed to be two words that I just put together. So in particular, if you have Z, for example, or any abelian group, so let's say, if you have, let's say Z. Z is an abelian group concentrated in degree 0. We can see always any group as a complex of groups where you have 0 goes to Z goes to 0, 0, 0, 0, 0, 0. This is a complex, successive differentials. When you compose, you get 0. So I see this concentrated in degree 0, degree 1, degree 2, minus 1. And so if I have, for example, R greater or equal than 0, I can look at this complex, and now I look at ZR, and how do you see this ZR? Where is this concentrated at? The quiz. So when I look at the jth element here, is the previous one at degree R plus J. So this is going to be 0 when J is different from minus R, and Z when J is equal to R. So this is concentrated in minus R, goes all the way to the left. And so now I'm going to tell you how, as an exercise, show that single cohomology, say from, say X, say with coefficients in Z, is the same as you look at in the world of homotopic, the homotopic category of complexes. So this is the same thing as maps, the homotopic category of complexes between this complex and this complex. Okay. Oh, okay, so what's the lesson learned here? Is that I started with topological spaces, I placed it in the homotopy category of complexes. Right, so now you have to check the literature, what does it mean? But basically the objects are complexes, and maps are homotopy classes of maps of complexes, all the differentials, commute, etc. And you use just that definition, and this follows immediately from what you know. And you can replace Z by any abelian group concentrated in degree 0, and that follows. But now the homotopic category of complex, if I replace this complex by something that homotopic equivalent to it, like a weak homotopic equivalent to it, I still get the same result. Right? So this homotopic, you just give an isomorphism. So let me give another example of such a thing. Let me give another example. And that brings us back to spheres again. So for example, if you have, you have an augmentation, so you have here C1 of x, so this goes to C0 of x, and C0 of x, I can think about it goes to Z, just a degree, because C0 of x is just, an element here is just a form of sum like these are points in x, and I send to the sum of ni. And let's look at the kernel of this. So we define C star tutor of x as just the kernel of this map of complexes, whatever, of C star of x to Z. So it's the same thing in every, except in the last one, I get the things with degree 0. And now claim, I can give a map of complexes. Is this the map from, say, ZR to this thing? And I put the sphere SR. This is smash product of S1 to S1R times. And if you forget about this and you compute the homology of this complex, what do you get? You get the reduced homology of your sphere, which means you just get Z in dimension R and 0 elsewhere, correct? So therefore this, and so basically you just look at one cycle that represents the top dimension called homology here and send 1 to that. And that's it. I gave you a map of complexes, which is an isomorphism in all degrees. And so these two complexes are logical, they are quasi-isomorphic. There's a map from this complex to this complex, inducing an isomorphism in cohomology, in the homology complex. Remember, I see everything as a cochain complex, so everything goes up. So in particular, consequence, so this induces an isomorphism in homology. So the complex, the all singular chains in X, this is something huge, much, much bigger than this, in some sense. But in terms of homological terms, they are the same. They represent the same thing. So, and then this implies that, for example, if I want to know the rth cohomology group of your space with coefficients in Z, I can certainly, I look at maps, and I'm avoiding the name derived category for the moment, but I could move on to the derived category. This would be just maps from X to this in the derived category. Right, because these two complexes are the same if you use this and the observation at the end. That's the usual definition of, if you track down the differentials and everything, that's the usual definition of similar cohomology. And now I'm seeing these two things. So what are we learning from here? So yes. Oh, thank you. I have to put a tutor here to get. I thought that the abstract topology in the audience is going to kill me. But anyway, the idea is that we send the objects in this world to a suitable sort of abelian category, or a place where I can do some homotopy theory or some homological algebra and realize singular cohomology as basically maps from this space, from the result of embedding spaces into that world, and a suitable element that represents represents cohomology. That's cohomology. And so now let me move on, because this is supposed to be one of the first things in my notes. In general, let me go back now to the classical homotopy theoretic world, and I'll take a bit faster now. I believe that most of you, the students, must have taken the Rebecca topology class with Marcelo, maybe Aguiar, and if you did, then Aguilar. And so you know exactly what I'm going to talk about. But so now back to the topological world. And this, I'm introducing this form because eventually I want to also talk about equivariant versions of that. Everything I'm saying here, we're going to say the same with the group attached to the spaces. Spaces with the group action. And of course, in the last, but ultimately the goal is to work with one of my favorite groups besides the trivial group, which will be the Galois group of C over I. It's a very complicated group. It's much more than you think. But so that will be the goal, to understand equivariant cohomology for this group. It's Z mod 2. Isomorphic to Z mod 2. É o mesmo pelo mais igual. Okay. So in here, you can talk about generalized cohomology theories. And so, and what are these theories? It's supposed to be theories over there. The idea is that you have a family for every n in Z, and now I emphasize Z, not on the non-negative ones. You have a family of covariant functors. H upper n, that sends, and then let me just put something for the moment, just to make life easier. Reduced, meaning that I'm sending based space, if you want, so a billion groups. You have those fun, contravariant functors. Together with a natural transformation. A natural transformation meaning that if I compose the n plus first with a suspension functor, remember that suspension, the suspension of a space is simply summation that space with a circle. Again, I'm placing special emphasis on the circle. So basically, this is say I take the n plus first homology of the suspension of a space, and I have a natural transformation from this. So let's say to the n cohomology of space. The natural transformation of functors. This is just representing suspension, which one of the axioms will be this is an isomorphism for every space. Now I'm also taking the liberty of saying top for topological spaces. You can assume there are spaces with homotopic type of CW complexes. Let's not worry that much about it, but that's what it should be. And so let's say the axioms are homotopy, variance, right? So the other one would be exactness, and the other one, what will be that? On the suspension axiom. So homotopy is that if you have two maps that are homotopic, map between spaces, base maps, base homotopies, if you want, then this implies that the functors that they induce are the same for all h r y to h r x, etc. Exactness maybe is something that yields exact sequences, but basically the idea is that if you have a map, it's very equivalent to saying have any map, could be for example an inclusion, and then you define mapping cone, whatever that is, I won't spend time on that, then you say that you have an exact sequence. So there's a canonical inclusion of y in here. Let's call it J. If they pull back to Hn of y, pull back to Hn of x, then this is the exact sequence. And then from this, the usual long exact sequence in cohomology follows in the standard textbooks in algebraic topology. Suspension means that this map, Hn plus 1 of S of x to Hn of x, is an isomorphism. The suspension induced by this thing here. And so these are the basic axioms. So then there is an extra additivity axiom that maybe I shouldn't spend too much time to Hn of the one-point union of spaces, which is the coproduct in this world. The inclusion of each of those factors induces a product, the composition of this cohomology. And then the last one is also isotropy, that if spaces have a weak homotopy equivalent, so if they have a weak homotopy equivalence, meaning something that induces an isomorphism of homotopy groups, implies that they pull back is still in homomorphism. So, I mean, those are extra axioms, but very useful for many things. And this forms what we call a generalized cohomology theory. So there's a set that makes it, how do you retrieve back what we started with in the previous segment? If I say, okay, the dimension axiom, if I add this extra axiom, if I add this dimension axiom, which is an extra axiom that says that Hn, and if I want to be really, really picky, I want to put S as 0 instead of a point because these are reduced theories. But so S in the 0 dimension is here. This is going to be 0 if n is different from 0. And then at n is equal to 0 is going to be some abelian group. If you do that in the category of spaces, whatever, so if you CW complex, there's only one theory that satisfies that. It's a uniqueness axiom. If you add the dimension axiom, then you get the uniqueness statement, right? That uniquely characterizes the theory. And then if you have seen the algebraic string rod axioms, then you can translate them, you can relate one to the other. There are many textbooks that do that. I guess George Whitehead's classic one does that. I think it was the first one to my knowledge that built on that form. More modern treatments and maze thing. But anyway, so this is the axiom that makes, and it should think about this as a point. Now we're going to eventually progress to other worlds where there are more points than only one point. And that's when things becomes more interesting. So, and so uniqueness, to describe the dimension axiom, that requires a little bit more input. So let me make a statement as a theorem. As a theorem, well, it follows from it's something called Brown, and this is, as I said, a crash course. The previous segment's more important. That given any such theory, right, any such collection of contravariant functors with all those properties, one can find a collection of, and this is all, let's stick to the homotopic categories about spaces that are like symmetric complex. We can find a collection of spaces in the same world. So let's say En on here, where N is only greater than 0, but together with some structural maps together with a bunch of maps, let's say structural maps. This is our S. And here I want to this is the R sphere, the M space, and then the map to the M plus R. And they're all compatible in some sense. Compatible to homotopic. And when I say compatible, I'm using the compatibility that, you know, SR smash SK is SR plus K. When you use this identification, then I'll have a bunch of community diagrams that make all those things compatible. And such that, and this is in our, this is all space, in the world spaces. Now, if you have a map, there's an adjunction, it's a little digression. So if the space of topological map, base maps, from when I smash a space X with a space Y to a space Z, this is the same thing as the same as sending Y, the functions from X to Z. Basic exercise in topology. But if you do that, then these spaces, they have adjoints, right? They have, so if you think about this as my SR, then such that, so this is called the digression. And the last condition is that when I look at the adjoints, let's say X to the head, I'm sending a map from my En to, let's say, the space. Now this is a compact open topology, so that we write like this. But let's call it R, E, N, R. Well, this is a space of base maps from the sphere. This is the R-fold loop space of this space. Right? So this is just the adjoint of his map. So this is space. This is the space of base maps from the sphere SR to this. But now I put the compact open topology, this is a continuous map, and I want this to be a homotopic equivalence. Okay, so this is a theorem that basically tells, I didn't tell, we can find these spaces and what the relation between this and the cohomology theory I just erased. The relation is that then satisfying. Now I say that the inf cohomology group. Okay, so I think the quick way to write is that for every integer R in Z, HR of your space X, let's say is the limit when, let's say, M goes to infinity. And now look at this. These are homotopic classes of maps from the suspension of your space Sm. And I want to be sure that I'm doing it right. Of X to our space E M R. Okay, So of course that my R could be negative, but eventually when I'm adding them, it starts getting positive. Correct? And what are the maps? So this is the colimit, the direct limit. Is that these maps, they map to, I can look at this suspension Sm plus 1 of x, and here goes my suspension S of Em plus R. But let's remember that the structural maps that I start with over here send one suspension when I add the indices. And so this thing maps down to Em plus R plus 1, and I can take this limit. So eventually the fact that I'm requiring that this is a homotopy equivalence basically says that I can stop as soon as I reach a positive number here. So it doesn't matter. So, but I want you to now think of the similarity between what I've done before and what I'm doing now. So is that I start with a space and I have a collection of other spaces together with additional structure, right? So a collection of this space and this thing and this, such that it represents that cohomology that you started with. So I'm trying to introduce this notion that yes, we can represent cohomology by sending spaces to a different category, and in that category do the homotopy theory, and we get out the theory that we want.
Excuse me, for instance, for the singular cohomology, what are these En?
Oh, very good question. Actually, that's the topic of what I'm going to do next. I'm going to give you a very concrete model. And so I think you have not taken the course with Marcelo Aguilar, right? Because I think the whole, they have a beautiful book, Aguilar, Prieto, and Gittler, where the whole approach to cohomology is based on this type of construction. And that's much more in sync with, we're going to learn in the last lecture we're going to present, that's essentially in spirit what guides Voevodsky's approach to motivic cohomology and algebraic geometry, which also eventually coincides with the isomorphic to Bloch-Hatch evolution in some circumstances. So this is, I think, a very nice way of motivating the path to that side of things. So, okay, so then let me answer your question now. So but before I do, let me give a name to this. So a collection of spaces with those maps, right? And then you may include this or not, you can always transform into something like that. This is called a spectrum. This term was coined by actually a Brazilian mathematician called Alan Lages Lima, but nothing to do with me, though. Everybody has to be the question. So it's a spectrum, and that is that given any generalized cohomology theory, I get a spectrum, but using this definition, given any spectrum, I get a theory. And the properties that I listed there follow directly from certain yoga out of this picture. So now let me go back to singular cohomology. So, and the idea, and that's why I did things the way I did up to now, is that, but let me give one example. So an example of a theory that's not singular cohomology. So for example, K-theory. So in K-theory, you can look at, you can define a spectrum where the first one takes Z cross a space, which is BU, and this is Z times BU. A way of seeing that is you take the limit over N and M in some appropriate way. Look at the Grassmannian, so of codimension N is Cn plus Cn. And they put inside one another by adding some subspaces to one side and then including the other and make it go off to infinity. And this is a way of constructing BU. And then I'll give another space, E1 is U. U is the infinite unitary group. And then E2, you go back to this. And then E3, you got the picture. So it's U or Z cross U, etc. And so what's interesting is that there is a map, right? So there is that when you take loops on U, which is precisely loops on E1, and then this is motor equivalent to Z cross U. And this is the main difficulty on this. It's called Bott periodicity. Bott periodicity has been an incredible tool for mathematics in this last century. And then, of course, that in the loops of E2, this is loops on Z cross U, but again, this is they're all basic stuff. So this is connected, and so this is the same thing as loops in U. And now this is standard yoga with classifying space of groups in some sense. This is back to you. And so which is then our E1. And you see that this goes on and on and on and on. So what's nice, this is a theory that it has negative cohomology groups as well as positive cohomology groups. And so the even dimensional ones are what we call the K theory, and the other one is the suspension. And so that's K theory. An example of a cohomology theory that's not the same as singular cohomology. At least one you can find. I think it was the first non-standard one. Here, I guess, out of Bott periodicity can answer that. So now, and anyone in the audience can correct me if I'm making any historical mistake here. So now let me go back. No, let me start over there. Let me go back now to this to what I had before. And so an example, so let's get back to say singular cohomology. So now, so let me introduce a definition. If you have X in space, and again, let's think about a CW complex, for example. And I define Z of X is just the free abelian group on your space. So far, this is just a set, which is freely generated, an abelian group freely generated by the points in our space. Let's put a topology on it. So actually, I want to put a topology where this is filtered by a collection of subspaces. So R filtered upwards. Where and now I am to be, at least this works pretty well when the space is compact. So let's start with this X compact. Otherwise, you take as a co-limit of those things. So let's not go into many details. But now think about this. I will take the disjoint union over all XR cross, let's say XI cross XJ. This is just the Cartesian product of X with itself. I times here, J times here. I plus J less or equal than R. And think about those are being like positive generators, negative generators, whatever for the. And then I just give a map from this to Z of X. When here I have, say, X1, Xi, I'll have Y1, Yj, and I take them to the sum of Xi minus the sum of Yj. Remember, this is the free abelian group generated by those things. And so the image of that are you can think about things that have at most, can be written as at most, R generators, some with negative signs, some with positive signs. Okay? And now give this, so basically the idea is that the image of that is what I call this of XR, and contain in here, give this, the image of this map here, the quotient topology from that, and then you start checking that the inclusion of one and all is a union of, actually in this case, compact sets that fills out your entire space. Well, that topology works fine with us, and then the fact is that Zx is an abelian topological group. Okay? And a theorem which is putting together other things theorem, I give many, you can put Dode and Tom and Mueller and whatever you want to put together to find a quick proof for this, but that is that when we define, let's say like Z with a 0 here as P. And remember, what emphasizes is the same thing as S1 smash S1 P times to be this abelian group, topological abelian group. But now I have to divide by a subgroup generated by a base point. Right? So I have a base point 0 on your sphere, and I just divide that. This becomes connected. Basically, this is equivalent to the connected component of this family. And show that they're the same. Then Z0 is an Eilenberg MacLane space. Space A, Z, T. In other words, when you look at, if you want to compute the pth cohomology of your space with Z coefficients, you just take homotopic classes of maps from your space to this thing. Homotopic classes of maps. This has a natural group structure because this is a group. These are maps from this intergroup. You just add one twice. It's the same. That answers your question. Not only that, if you have a different group, actually you have Z mod P, you can really tensor this with Z mod P. And then if you have a finitely generated group, you just take products of that. Otherwise, you take a direct limit of finitely generated subgroups when your group's not finitely generated. Now, and I'm going to even sketch the proof. Of course, I won't give details. But what I want you to do is to contrast this with the previous approach, right? Which was homotopic class of maps from C0 of X, not C0, C star of X, to what I call C star tilde. That's the tilde that accounts for the 0 here of this here SP. And I take homotopic groups, but not in the category of complexes. Homotopic maps of complexes between these two as opposed to spaces. So now the proof, and then I will use this to jump into this ROG graded cohomology theories, which are equivalent cohomology theories with an action, but the grading is slightly different. So the proof is the following. So step one is that for every CW complex, this thing has homotopy type of CW complex. I can prove that for anyone if you ask afterwards. Next. Dalton theorem. It's actually, this should have a display of its own because this is really what motivated a lot of what comes next. But Dalton theorem says that if you take the homotopy group pi j of this group here, if you put this 0 here, with based at 0, this is isomorphic to the reduced homology J of X with coefficients in Z. So this is a very, very, very beautiful theorem. And as a consequence, so this implies that if you take X is equal to SP, then we're saying that pi j of my Z0 of SP comma 0 is isomorphic to the homology of SP reduced. So it means that it has only one non-trivial homology group, which will be Z when J is equal to P, 0 when J is different from P. Now I'm going to cheat. I'll say that any space of the homotopic type of CW complex that satisfies this condition is a K ZP. So in other words, this property characterizes uniquely up to homotopy, of course, these spaces that I'm looking for. And now, of course, I can give you links for the literature where you can find the details. But I wanted to really bring forth the Dalton here. So now what I like to do is say, okay, now I have covered several things. I made a basic review of generalized homology theories. I told you how to find a space that classifies homology. Let me tell you a little bit about what about the spectrum. I said I can find a space and I can find those maps from one to the next. I didn't show you how to do that, but this is called the Eilenberg-MacLane spectrum. And I'm just doing with Z. I'll simply remember that I have my A E sub P, or should be KZP, but I'm using the previous notation, is just the free abelian group on your sphere SP, but mod the things that are pleasing the point. So what I want to do, I want to send a map from S1 smash EP to EP plus 1. But basically what you do is that if I have a T in S1, and then what are elements here? Elements are sums of things like this, Ni, Xi, or the sum of the Ni is equal to 0, for example, and then you just send the sum of, now by Si belong to the sphere SP, you send the sum of Ni, T smash Xi. Wait, now this now belongs to the sphere SP plus 1. And that's the spectrum. This is Z0 of SP plus 1. And this is 0 of SP. And so I do give the maps in the Eilenberg-MacLane spectrum that you can use to classify homology fields. Now let's change gears. And let's say, okay, now I want to complicate life. I want to start with the equivariant world. And I want to somehow introduce the notion of generalized homology theories. But now I want to introduce a special one. So this is not going to be only the so-called Borel homology, the equivariant homology that you're very used to, but there will be actually generalizations in the ordinary case of things that are called Redon homology. Again, Marcel has done a lot of work on that. But in particular cases, it extends to something that's called what it's called RO graded homology fields.
So Pablo,
I will explain. Yes. Go ahead.
say something about this.
Yes.
When you use this bound representation theorem, you get an omega spectrum. So when you get your definition for cohomology, associated with spectrum, you can take just maps to the n space. You don't need that limit because that limit outside.
Yes. The only thing that I wanted to do that is that because when you want to define the negative cohomology, then I would have to do something like, I would have to take the n suspension of x and then match that to the E0. You're right, I said it.
Yes, you put the n loops on the right.
Yeah, I put n loops on the right, exactly. No, I agree with you, I just put the limit because then I didn't have to explain anything.
But the problem is that if you, the limit outside, you will have trouble if your x is not fine, if your space is not compact.
Sure, I agree with that. So a lot of water on the right. I know that you have to be very, this representability works pretty well when you're doing everything over the, finite Sadami complex. Absolutely. This is just, I said, a crash course with a lot of good stuff. But so here, now, I suppose that let's start with the G's, with the finite group. And now I'm working with things that are spaces with an action of G's, G spaces. So this is the world of spaces, a G action, and then G equivariant maps. And all maps are maps that are. And then, if I want to, do homotopy theory, so I have to make, homotopies, like, are maps between spaces, and for every t and I, so for every t, this space is still a G map, a G equivariant. So everything now respects the action of the group. What I have in mind for the future is, suppose you have a bunch of equations, polynomial equations with real coefficients, right? And then you look at their complex solutions, and you do know that if you find a solution, its complex conjugate is also a solution, right? So then the action of the Galois group makes this complex solution into a space with the action of Z mod 2, the action of the Galois group. As trivial as it sounds, this is really important because there are certain, look at this. For example, let's look in projective space. So if you look at this equation, this is an equation in P2, right? This is a conic in P2, and everybody says, oh yeah, sure, it looks like a projective line, right? Embedded in P2. Give me one real solution of that equation, projectively. None. So this is an example of the scheme over R that has no real points. So what's important, but what differentiates that from the the projective line is the action of the group of the complex points. This is a perfectly nice scheme, but as a real variety, this is very different from the projective line. So that's I want a cohomology theory that can pick up that difference, right? So you understand that. So now, I think about the 1970. In the International Congress of Mathematicians, Graham Siegel made a statement that was carried through, several years later by many people, Peter May, his school, etc. That equivalent cohomology theories should be graded by the representation ring, or orthogonal representation ring, the ring of orthogonal representations of your group. For example, think about a trivial group, right? So what are the representations of the trivial group? Right, there's the ring of representation of that. Just the integers, right? So the vector space, what isomorphism class of vector space? Because any vector space is a representation of your group. And the isomorphism class of vector space is just its dimension, right? Dimension. And so the integers. And that's why the cohomology theories I described before, they're all graded by integers. So what does it mean? That means that we have, what is such a thing? Is a collection of contravariant functors. And now let's say H upper alpha, let me put a G over here, from the category of spaces, right, with an action to a million bits, where alpha is an element that belongs to the representation of G. And so what are the axioms? Axioms, of course, it has to satisfy its contravariance, right? But it has a homotopy axiom, meaning that if I have two maps that are homotopy, true homotopy like that, they induce the same map between any of these two. Now, homotopy exactness in the same way. Now here is what becomes interesting, is what we call the suspension axiom. And again, this type of suspension in funny directions, as we say, appears in the motivic cohomology as well, as a bifurcated theory. And we're going to get there, probably examples of these will come up on in a second lecture. But
excuse me, I cannot understand how do you write exactness spaces. I don't know, because you have an ordering and alpha.
Well, how did I write exactness, right? Suppose you have a map. Suppose you have a map F, equivalent map between two spaces. And then we can, out of that, we also can include this in the mapping cone of that map. And I said that then, for every alpha, you, in the representative here, you have that H alpha of TF. You take the pullback to the H alpha of Y, you take the pullback to the H alpha, and that's the beauty of writing this way, is that I don't have to deal with alpha plus 1. For all F's, and for all alphas, and for all maps, this is exact in the middle. Now you say, okay, that's cheating. I want to know, well, how do I get an exact sequence out of it? Well, once you fix the alpha, if you want to do, say, the old classic thing, is that you can really define the cohomology for a pair, right? So, for example, X is the subspace, and then, goes to H alpha of X, goes to H alpha of the subspace, and then goes to H alpha plus one copy of the trivial representation, so it's a 1, of XA, and that is coming. So for every alpha, we have such a long exact sequence, and that allows you to make the calculations. But that follows, that stems from this. Okay, so, all right, so I defined, but what's suspension now? What's suspension is one of the most interesting axioms, suspension. Suspension simply says now it's different because, so let V be really an actual, be an orthogonal representation of G. All right, so in a vector space, a real vector space on which G acts by automorphism, and then denote S upper B, actually the one-point compactification of a sphere. This is really a sphere, but now we have embedded a group action. This group action fixes at least infinity of 0, but I have this group action on this sphere. So it's an equivariant space, sorry, the space with an action, denote this. Then, so we have natural transformation well, now I have my HG alpha composed of the functor that smashes with my sphere, and that goes to, I'm sorry, let me go the other way around. In such a way that such that when I do H alpha plus V of G of S V of your space, this is really smashing our space with a sphere. This is now a space with a G action. This is actually isomorphic to H alpha G of X. So think about this, right? Look at it. If the group is a trivial group, then representations are just in integers. So an actual representation, not a virtual one, then you would have to have a positive dimension. I don't know, maybe vector space is negative dimension. But so that would be some sort of an Rn, and then of course when you add infinity, this is your Sn, and then successive compositions of the previous statement gives you this. But now this is for all alphas and v's to get these natural transformations. So I guess my time is up. But I will start my next talk discussing this type of theories, especially the examples pertinent to us in the case where, for example, G is equal to Z mod 2, then when you look at the orthogonal representations of Z mod 2, there are only two irreducible ones, right? You have a trivial one, a trivial representation, so I can take any direct sum of elements like this, a copy of Z, and you have, the alternating representation, the sign representation, whatever you call that, like that. And this looks like, for example, complex conjugation. If you look at C, for example, the complex numbers, this is R plus IR. This part, as a representation of the Galois group, of Z mod 2, is just 1. And this other representation is what I call C. So you see the complex numbers corresponds to 1 here and 1 here. And so in some sense, the alphas that I'm using here, when you deal with the Galois group of C over R, I'm going to have only two integers, N and P. And if you do it the right way, they correspond exactly to the motivic N and P in motivic cohomology for real varieties. So we'll continue that next time.